Hello, welcome back. This is our video solution to problem 12 from Superquiz 3. This was the problem which was optional and assessed your understanding of equivalence relations. So in this problem, we're going to define a relation on the point on the surface of the unit sphere. So we denote the sphere by the Greek letter capital sigma. So again, it's the unit sphere, so it's given by x squared plus y squared plus z squared equals 1. And we're centered, of course, at the origin. So the relationship we're going to define, which we're calling A, is given in the following way. If you have any 2 points on the sphere, x and y are going to be related, that is, the pair x comma y is an element of A. If there's a straight line that goes through the points x, y, well, that would all, if you just stopped right there, like that's always going to be true. You take any 2 points anywhere, you can draw a straight line through them. But we want that straight line to also go through the origin. So it could be helpful here to draw a picture. So if we draw our x, y, and z axes, and we put a sphere around this. Of course, the origin, oh, it doesn't look like it went around it very much. There's the origin right here. And if I have 2 points that are going to go through, the 2 points on the sphere, and there's going to be a line that goes through them and through the origin, then they have to be what are called antipodal points. So say I pick some point on the surface of the sphere. There is a unique line that goes through that purple point on the surface and through the origin. And then it's going to have to come out the other side, right? It keeps going, and it's going to hit a point which is on the bottom half of the sphere and on the opposite side. Right? And these 2 points that you get, those are called antipodal points. And maybe you start to understand why I use the letter A to denote this relation. So if you have antipodal points on a sphere, then they're related. So we want to show that this is an equivalence relation. So for A, we first need to show reflexivity. And this is pretty clear because if I have my point, let's call it x, I know there exists a line that goes through x and x, I mean, it's the same point, and the origin, right? That's a fundamental axiom in Euclidean geometry. Between any 2 points, there's a straight line. Right? So between x, so here x is some, we'll take 3 elements, x, y, and z on sigma. Between x and the origin, and let's abbreviate the origin with just a nice O. So between x and the origin, there exists, in fact, a unique straight line, although we don't need that for reflexivity. Hence, x comma x is an element of A. Okay, how about symmetry? So for symmetry, we want to show that if x comma y is an A, then y comma x is an A. So let's start with if x comma y is an element of A. Well, that means that there exists a straight line through x, y, and O. So then there exists a straight line, right? And I'm using straight here because sometimes when you're working on spheres, you might want to talk about lines as being great circles. So I'm distinguishing here by using the word straight. There exists a straight line through x, y, and the origin. But of course, this is also a straight line through y, x, and the origin. Right? Not necessarily in that order, but it doesn't matter. Which is also a straight line through y, x, and the origin. Thus, y comma x is an element of A. All right, so reflexivity and symmetry are very, very simple there. They're almost tautological here. So how about transitivity? Maybe this is more complicated? Yeah, probably not too much more. So for transitivity, we're going to assume that the pair xy and the pair yz are in A, meaning x is related to y and y is related to z. Okay, fine. Once I know that x, y is in A, that means that there is a line that goes through x, y, and the origin. Okay, so then there exists a straight line through x, y, and the origin. However, a sphere and a line are going to only be able to intersect in at most 2 points, right? Essentially, you can think about this as you're trying to solve this equation, right, where you have a quadratic, which the sphere is, and this line, which is linear, and there's only at most 2 ways to solve that equation. So there's only going to be at most 2 points on this line. On the other hand, we also know, and there exists a straight line through y, z, and the origin. But it has to be the same straight line because 2 points determine a line. And both of these lines contain the same 2 points, y and the origin. So as 2 points determine a line, and as both lines contain y and the origin, we conclude they're the same line. But again, a line passing through the sphere can only hit in at most 2 points. So y here, okay, those are the same points. What could this be? Well, x and y, they could be different, but that's 2 points then. And so z could be either equal to y or equal to x. Those are the only options. If it's equal to x, then you're really just asking, does yx, or is xx going to lie in A, which we know it does. If it's equal to y, well, then we're asking, is xy in A, and we know that is true as well. So let's collect this. So thus, z, well, I guess there's a third, okay, there's one other option here, right? So let's make this very systematic here. All right. If x and y are already the same, then z could be something different. So either x equals y, or let's see, x could equal z, or y could equal z. So those are the 3 cases we have. So in this first case, if x is equal to y, then we're asking, if we know that xx and xz are in A, does that imply xz is in A? And of course, it does, because we just set it over here on the left. xz is in A. All right, so yes. Okay, what about if x is equal, so this was x is equal to y. What if x is equal to z? So then we have zy and yz are in A. Or if we like, we keep everything as x's, that's fine. xy and yx. And we're asking, does this imply that xx is an element of A? Well, it's not one of the 2 that we're given, but this is the reflexivity that we've already shown. So yes, by reflexivity. Okay, and what if y is equal to z? If y is equal to z, then we have x comma y and y comma y are in A, and transitivity would ask, is x comma y in A? Well, yes, because we have it right here. So yes. So in all cases, transitivity holds. Therefore, we get transitivity, and we conclude we actually have an equivalence relation. Okay, so we had some other questions though. We wanted to find the equivalence class of 0, 1, 0. So let's see, that means we're looking at, actually, let's get a little nice red dot here, right? That point, right, it's at 1 on the y-axis and 0 and on the x and z axes. So to get the equivalence class, we want to know all of the points on the sphere that are related to 0, 1, 0. But what does it mean to be related? It means you need to be on a line that passes through this original point as well as the origin. And there's only one such line. And it's going to hit on exactly the opposite side of the sphere at the point 0, negative 1, 0. So this equivalence class for the point 0, 1, 0 just has 2 points, itself and its antipodal point, 0, negative 1, 0. Okay, so finally we're asked to find a transversal, i.e. set of representatives, for the quotient set, which essentially means we need to find one representative from each equivalence class. All right, well, let's take this picture. Let's redraw it down below, give ourselves a little room. So here we go. We have our nice sphere. And what we know is that, well, let's see, let's draw that a little bit around. There we go. What we know is that if you take any point, say in the upper hemisphere, so say I have a point up here, there's going to be a unique line that goes through the origin. All right, so this comes out here. It's going to go through to the other side. It's going to hit the sphere and then pop out. And that will, if I started with something in the upper hemisphere, it's going to go through the origin and then end up on the other side in the lower hemisphere. So the antipodal point, point of any point in the upper hemisphere is in the lower hemisphere. So if I'm looking for one element from each equivalence class, I don't need to take any point from the lower hemisphere because it will have a corresponding point in the upper hemisphere that I can choose. So, and in fact, anything I take in the upper hemisphere, right, we know that corresponds to something in the lower hemisphere, so there's no repeats there. So what I can do is just take the upper hemisphere, except for one little exception. What about this ring around the middle? Well, with the ring around the middle, if I choose some point here, I go through the origin, and it'll pass out again on this ring behind it. So there, I'm not going to in either case be in the upper or the lower hemisphere. So what I'm going to have to do is choose exactly half of these points, right? So I can start at one end. So maybe, for example, we'll come over here. And I need to just go halfway around the circle. Each one is going to correspond to a point on the back half, right? If I take, say, this front half. Now, the only place I have to be a little bit careful is where I start and finish. Because, well, if I go right to this is our 0, 1, 0 point again, over here, I don't want to include its antipodal point over here. So I'm going to make sure that I put a little circle right there. So from this we see a transversal of the sphere modulo this equivalence relation consists of all points in the upper hemisphere So if we wanted to write that out more formulaically, we could say, okay, take all points x, y, z, such that z, we want that to be positive, so that tells us we're in the upper hemisphere, and we want to be on the sphere. So x squared plus y squared plus z squared is 1. Okay, so all those points, union, so along with, so I'm going to take here all the points on the unit disk such that I'm not in the back half of this picture. So in this picture, being in the back half means that the x would be negative, right? So we're going to say all points on the unit circle in the xy plane with positive x value. Okay, now if I say it like that, I'm going to be leaving out this one point here. So we'll have to include that. But let's write this again. So this is all xy 0 now, such that the x is positive and x squared plus y squared is 1. So then along with, and now here's our last point, along with 0, 1, 0. So that's the one point where the x isn't positive, but that lies on this unit circle, right? That we don't want to include both of these, but we'll include one of them. Of course, we could choose the other one if we liked. All right, so that was kind of a long video. It's because equivalence relations, well, they require some explanations. So hopefully this is helpful.